All right, guys, we are beginning our last little section here for conics. And this is us learning about hyperbolas. Hyperbolas, they kind of look like two parabolas that face away from each other. They kind of have that idea going for them. But it's what they are is it's just a set of all points in a plane whose distance from two fixed points called foci have a constant difference. So it's very similar to the definition that we had for ellipse. Let me see if I can pull that up here so you can see the similarities. But here we go. Let's see, ellipse, it was the set of all points in a plane whose distances from two fixed points have a constant, there's the one different word, sum. Having a constant sum or a constant difference, that's what makes the difference between hyperbolas and ellipses by definition. So the different components of a hyperbola you can kind of see on the pictures here. So you'll probably want to pause the video and get a nice picture drawn and all that stuff. But we have, again, those foci, that's just plural for focus. So there's two focus points. And this time, you know how they were before, they were inside the ellipse. Okay, now we're going to see these. They're kind of inside the hyperbola, but like they on the outside of those vertices, kind of like, so it's the structure of it is different. So they're inside the curve, right? Just like they had been inside the curve for a parabola and an ellipse, but it just is kind of a little bit of a different setup here because on ellipse, we had this type of deal where we had our vertices and then the focus points were closer to the center than the vertex points were. This is switched around. They're further from the center. I guess that's what I was trying to get at. The focal axis, same type of thing we had before. So a lot of these definitions, honestly, are the same type of definition. Vertices, the point where the hyperbola intersects the axis. So we've got that. The transverse axis and the conjugate axis. This is what we can kind of compare to the major and minor axes for ellipses. Remember those? It's a kind of a similar concept where the major axis had been 2a, the minor axis had been 2b. The transverse axis is kind of comparative to that major axis. That's the one that's 2a. The conjugate axis is the one that would kind of compare to the minor before, and it's 2b. Kind of. So anyways, the transverse axis, just like the major axis, connects the two. One thing I will point out, the A value does not have to be more than the B value. It's actually something I've added as a little note in orange down here. I don't know how well that's showing up on the screen, but A does not have to be more than B for a hyperbola. It can be the other way around, which is probably a good reason why they're not calling this major and minor axes, right? Because then that would make you think that, but it's not the case. So these can be different sizes, and that's fine. So again, the transverse axis is the one that connects the vertices. That's what you want to look for. The conjugate axis is the one that does not connect the vertices. It's perpendicular. It goes to the center. Okay, so remember this symbol right here means perpendicular anytime that you see it. It's just a long word to write, easier to write the symbol. So, and it goes through the center point. So wherever those axes cross, that's going to be at the center. Okay, that brings us to our Pythagorean kind of idea, which is different than the one for the ellipse. This one is actually more like what we're used to seeing with your Pythagorean theorem. They've got it in a different order, but it's the same actual equation. This is c squared equals a squared plus b squared. So be careful when doing problems because it's very easy to mix up which equation is for what type of shape and all that kind of stuff. All right, now you have two different cases. You can have a hyperbola where the center is at 0, 0. You can see that right here. Or you can have it somewhere else, like this guy. Now, I know these pictures, like one of them is opening sideways and one is opening vertical. In both situations, we're going to see horizontal and vertical. So just keep that in mind. You're going to see formulas for each type and all that stuff. So watch out for it. Another fun feature about hyperbolas, which I have not mentioned yet, I've kind of got it shown in dashed lines, but it's a little bit more clear on these. You'll see these little dashed lines that are going. Those are little asymptotes. Those are where the hyperbola, it's like approaching but not crossing, approaching but not crossing. And so we're able to find those asymptotes, and I have equations for those too I'm about to give you. All right, so without further ado, let's look at the equations for your hyperbola centered at 0, 0. That's what we have right here. So I'm sure you'll want to pause the video and look at it in all its glory. But this guy, let's zoom in a little bit more so we can see this better. All of those exponents, if you're wondering what my handwriting is saying, all the exponents are little 2's. And we have a set of equations. Again, this is center 0, 0. And we have a set of equations where we see it open left or right. And we have a set of equations when it opens up or down. So I want you to see if you can tell the difference there. Remember how we've said that it doesn't, A does not have to be more than B. It can be, but it doesn't have to be. So how do we know the difference? So the difference between the two different situations is look at what's positive and what's negative. I mean, that's probably your best bet here. What's being subtracted or what's positive. So when we see that this is going to open left or right, the x squared fraction is going to be positive, while the y squared fraction is going to be negative. And if we see that it's going to open up or down, then see that vertical axis, you'll see the y squared first, so that it's positive, and we're subtracting the x squared. So if you see it's going to open left or right, in standard form, we will put x squared first, and that's because it's the positive fraction, and y squared is the negative one, so it's just easier to write it that way. And so you'll see x squared minus y squared. And then the vertical one, opening up or down, you're going to see y squared minus x squared. So those are your little standard equations, or the standard form of the equation. And then you have all these other features. As usual, C is talking about the distance from the center to a focus. So you're going to see, in this case, C is going to be more than A because it's further away from the center. It's a little different than it was with ellipses. But your foci, we're still going to follow those same kind of ideas that you had. They're the exact same ones from all of that for the foci and the vertices, the exact same pattern. It's just that your C and your A, they have a slightly different relationship. So you'll end up seeing C is always going to be more than A and all that kind of stuff. But you still have that same pattern. As long as you have C, you can get your foci. As long as you have A, you can get your foci. And then we've had this lovely addition of those asymptotes. There are 2 of them. That's why you see plus or minus, because you have one that's going to have a positive slope and one that has a negative slope. And you're going to have your A and your B value, okay? And you're going to make a fraction out of them. They're what's going to give you the slope of that line. So for the ones that open left or right, you're going to have plus or minus B over A, x. And then if it opens up or down, it's plus or minus A over B, x. Okay. Then we have another set of equations. What if my center is instead at HK? What do we do? Well, here are my equations for that. Okay. So if my center is at HK, then we really just have the same situation we've had before, where we're going to subtract H in that little binomial with x, going to subtract k in that little binomial with y. Otherwise, it's the exact same structure. You have the same equations, even for your equations for the foci and the vertices. Those are exactly the same thing. So it's not necessarily having to learn a whole new set of rules. It's just that this equation from the get-go has been changed a little bit. And we have these asymptotes that we're kind of including as well. You can just see the transformation part here. That's all that this center does, is it transforms it to a new location. So you can see this x minus h, that's moving this horizontally, and then the plus k moves it vertically. And so anyways, I think I dropped my plus or minus in front of that other one. Let me fix that. I got carried away, missed it. There we go, plus or minus in front of that one too. Okay, otherwise, all good, all the same. So that is all the equations and all of the different features of our hyperbolas. And again, A does not have to be more than B. We'll do one example here, but then we'll probably save the other ones for another video because we'll probably put them in a different lesson in class. But we'll go ahead and do one here since we've got plenty of time for it. Oops. All right, just trying to get it situated. Okay, so here we've got example 1, and it says find the vertices and foci for this guy right there. And I don't know if you guys recognize this at all. We actually have seen this same type of equation with ellipses. The only difference was that we had a plus between them, if I'm remembering that going correctly. Yeah, it's the exact same thing, just with a plus. So we're going to kind of see how this compares, and you can kind of flip back in your notes if you want to see how that compared to the ellipse problem. The first thing we're going to do is we're going to get this put in standard form, because right off the bat, I don't see necessarily where the center is. You might make a good assumption, but it's not in standard form, and so it's hard to see what the A value is, the B value, and then how would you find your C to get this foci, so you need to figure that out first. So the first thing I would do, let me rewrite the equation down here where I can work it easy. We've got 4x squared minus 9y squared equals 36. And so what we're going to do with this is we're first of all just going to get this put in standard form. And just like it was when we dealt with the ellipses, standard form for the hyperbolas always is setting these equal to 1. So we're going to do that. We're going to make sure it's set equal to 1. And the easiest way to do that is just to divide by 36. Okay, then we can reduce these fractions down. So 4 goes into 36 9 times. 9 goes into 36 4 times, and then we'll just get a 1 out of that. So when I rewrite this, we'll have x squared over 9 minus y squared over 4 equals 1. This is the standard form of the equation, and remember that we always want the minus to be between the two here. So if you ever worked it out and the negative happened to be in the very front of the equation, then you would need to rearrange that because we do need the minus to be between the two if we're in standard form. That's the biggest indicator as to what's your A and your B. It's not just which one's the biggest, which is what we had on the ellipses. Here, which one is our A? Well, that's the one that came from the first term, the one that was a positive fraction. And our B comes from the one that was subtracted. So again, it's a little different than it was last time with getting the A and the B. But I can say here that A squared is equal to 9. So A is, and you could say plus or minus 3. You also could just say 3 since 3 is it's supposed to be just a distance. So it's fair to say that it's just 3. B squared equals 4. B would be plus or minus 2. Or again, you could just say 2 since it's supposed to indicate a distance. That's fine. Okay. All right, now to get C, the equation, if you recall for this one, is a little bit different. You'll see it right above your foldable, right? C squared equals A squared plus B squared. So it's a little bit different for this equation, but it's more familiar to Pythagorean theorem. So I'm going to work that right here. C squared equals A squared plus B squared. And I'm just going to go ahead and plug in. We know A squared and B squared, so I'm going to go back to those. C squared equals 13. So C is going to be square root of 13, and that will help me with getting my foci. So again, the question had said to get the vertices and the foci. In order to get vertices, I need A. In order to get foci, I need C. I also should know where the center is. Can we tell? Looking at this equation, I don't see anything added or subtracted in the top of my fraction. So I'm seeing for these, this is center at 0, 0, because there's nothing added or subtracted in the numerator. I also can tell that this is going to be one of those that's going to open left to right, because it's the x squared that's written first, and then the y squared is the one with the negative that's being subtracted. So we're going to say open left, right. Okay. And we should be able to use the correct set of equations to get our foci and our vertices. So I'm going to bring these up. These are the ones we're dealing with. We got foci and vertices. So it should just be for the foci, plus or minus C, 0. And then for our vertices, plus or minus 3, plus or minus A, right? So let me pull those numbers from our problem. Okay, vertices, plus or minus A. So that's plus or minus 3, 0. And then for our foci, we're going to look at our C value, plus or minus C, 0. That's what it asked for. Okay. So as far as just like getting a singular problem down, this is probably what I would expect us to get through in class. And if we got through a little bit more, that's okay. But this is, and it'll take a little while to get those notes written down. So my guess is this is as far as we'd be able to get. So definitely, if you're going to miss class where we're going through the rest of the examples, definitely make sure to watch the next video when it's posted. But that is going to be it for this one. I'll see y'all in the next one. Bye.